Okay, welcome to Emergent States of Matter, March the 17th. Today we're going to take things to the next level. So let's remind ourselves what we were doing at the end of last lecture. So what we were trying to do was we were trying to calculate what happened in a weakly interacting Bose gas. And the way we started to do that was we start off with the Hamiltonian, which is somewhere where miles back. Okay, here's the Hamiltonian. Well, yeah, something like this. Here's the Hamiltonian in the pseudopotential representation. What we discussed last time was how we can, in a Bose-Einstein condensate situation, the condensate itself, because it has a large number of particles, essentially behaves like a C number, a classical, a complex number, not an operator. And so we write down the field operators as the sum of a complex number which represents the condensate, and then operators for the excited states. And then what we did was we worked out what the sum over all the k's were. We wrote down the Hamiltonian, and we expanded about the Bose-Einstein condensate in powers of the annihilation and creation operators up to second order. Now, our goal is to try to get a quasi-particle Hamiltonian, but the problem is that our Hamiltonian has terms that do not look anything like quasi-particles. They do not look anything like number operators. They've got all sorts of terms like A dagger, A, and so on. And so, so the strategy is to try to find some kind of transformation that will diagonalize this Hamiltonian. And once it's diagonalized, then by definition of diagonalization, it will end up in the quasi-particle form. So what we did was we introduced a transformation which is basically a rotation in the space of annihilation and creation operators. And that's written down here in the middle of the screen. So we defined these new operators, alpha, which were linear combinations of the A's and A daggers. And the coefficients were complex numbers, which I called U and V. And there's some arbitrary functions. I'm at liberty to choose this transformation any way that I like. And what we're going to do is choose this transformation in a way that is really very, very clever and enables us to do a very powerful calculation. So what we did was we simply wrote down this transformation. And then the first question that we asked was, well, can I make this transformation be invertible? Can it have an inverse? And so what we tried to do then was say, if I know alpha as a function of A, then I should be able to calculate A as a function of alpha. And the way that I inverted it was just to simply use a trick. Just noted that if I take the first equation here and multiply it by V, and the second equation multiply that by a U, and then I can subtract them, then what happens is I get on the right-hand side this term over here, and so then we said, well, we've got two constraints. We've got two unknowns, and we can apply some constraints for anything that we choose. So let's choose UK squared minus VK squared to equal 1. Why not? Let's just do that. So we did that. And of course, then that makes it very easy for us to invert this transformation, because what it means is that I simply now have a formula for the A's. This is the equation star back down here on the left page. I now have A in terms of alpha and alpha dagger, which is what I wanted to invert the transformation. So now in the middle of the page there, you can see the result of inverting that transformation. Now, the advantage of doing it this way is that now I know A as a function of alpha. Then what I can do is I can substitute the A's into the formula for the Hamiltonian, and then get an approximation for the whole Hamiltonian. And so let's just we're going to go and do that right now in a few minutes, and the algebra is going to get quite hairy, so I want to warn you about that. But the first thing that I want to do, and this is what we ended in last lecture, was to understand physically what this constraint means. So what we decided to do was have a look at these operators, these alphas that we've introduced, and ask ourselves, well, what do they physically mean? And one way to answer that is to look at their commutation relations, because we're used to operators having a simple particle interpretation, and so that they are eigenstates of parity. So we know we expect to have either bosons or fermions, something like this. So what we did was we just plugged in, we took our definition of alpha, as you see here in the middle of the page, took the definition of alpha with u and v as they are, and just simply calculated the commutator alpha alpha dagger. And what you can see is just by using the rules of computation that in fact what this thing turns into is just alpha alpha dagger is just equal to uk squared minus vk squared. And that was exactly the constraint that we applied to these u's and v's in order to make the transformation invertible. So what we've learned then is that by making the transformation invertible, these alphas actually obey Bose commutation relations. And so they correspond to some bosonic particles. So what actually do they correspond to? Well, that's what we're going to see now. So what we're going to do is we're going to go ahead with the calculation. I'm going to show you this now. And what we're going to end up with is I'm going to show you that the Hamiltonian will end up looking like this. It'll end up looking like a quasi-particle Hamiltonian, a Hamiltonian that describes an energy plus some number operator times an energy spectrum, and so it's a bunch of free particles added together, and that's what we mean by the quasi-particle Hamiltonian. And we talked about this at the beginning of this whole section. So let's do the calculation. So this is now what I'm going to call step 4. So in step 4, what we're going to see is that what we're going to do is now substitute the formula for A as a function of the alphas into the Hamiltonian. So specifically, when I say the Hamiltonian, what I mean is this particular functional form that I have right over here. So that's the Hamiltonian, and that is up to quadratic order. So let me write, I'm now going to write down the formula, and it's going to be a complicated formula and I may not even be able to fit it onto one page. So bear with me as I write it down. What's important is not that you check the algebra and make sure I've got a factor of 2 right or something like this, because I guarantee that I have got it right, but I want you to understand the logic here. So warning, here comes a really long equation. Okay, so here we go. By the way, this isn't the longest one that we're going to encounter in this course. You are going to do in homework a calculation for the BCS theory of superconductivity, and it will involve exactly the same steps as the ones I'm doing now, but the algebra will be twice as complicated because you've got fermions. You've got paired fermions making a Cooper pair. But don't worry about it. It's all very simple. So here's what the Hamiltonian turns into. So all I'm doing is taking this equation up at the top here and substituting in my linear transformation. So, and then I'm just regrouping the terms, and I'm regrouping the terms in a way that makes sense. So let's go ahead and do that without any more approximation. And let me try to write them down in different colors so that we have a chance of being able to sort of see what we've actually done. All right, so. Okay, that's the first term done. So that all went well without any mishap. So that's good. Now comes the second term. Okay, that's the second term done, and now the third term. You should start to get worried when I'm using 3 different types of typography of brackets. That tells you that it's going to be messy. So, and it is. And let me just make sure that you see that this is exactly what it's meant to be. Let me write this term again. Okay, and then close that bracket, and then close that bracket. And then I'm done. So then of course there's higher order terms, which are going to be of order alpha cubed, which we are neglecting, and those alpha cubed terms come from the a cubed terms that would have been there. All right. So now let's have a look at these terms, and so let's put them over on the left-hand side. Okay. And why don't I give these terms a name? So let's call this line A, this line B, this line C. Okay. So let's have a look at the term A. And so what is this thing? Well, it's basically a number, half n u naught n, plus a sum over k or a bunch of functions of k. So it's just a function. And it's the sum over k of a function of k. So it's basically just a number. Okay. Term B. So what kind of thing is that? Well, it's a sum over k of some god-awful mess, and then alpha dagger A, alpha dagger alpha, alpha dagger alpha. So the 2 terms here, so it's basically a sum over k of some mess that depends upon k times alpha k dagger alpha k. And of course, I've got the sum over k and the sum over minus k separately, because last time I separated them out. And so this thing is in fact, is a quasi-particle term. Because this thing over here is nothing more than just a number operator. For these alpha particles, whatever they are. So this is the number operator times something or other. And we know that what that interpretation is going to be is that the interpretation of the thing that's inside the bracket is going to be the energy, because this is the total energy of the system. So it's equal to the number of particles in state k times the energy of those particles. So that's going to end up being an energy. And then I've got term C. And then term C is a kind of, what the heck is this, right? So it's just a mess. It's nothing that we recognize. So what we say is, well, no problem. We still have one constraint to use. So we don't know what to do with this. So what we're going to do is we're going to use our remaining constraint on the u's and v's. Okay, remember we've got two constraints. One of them was uk squared minus v squared equals 1, but I need to determine those functions. So what we're simply going to do is we're going to just simply set term c equal to 0. So we're going to simply, to set it equal to 0, what that means is, i.e. set the term that is in the square brackets equal to 0. And the term that is in the square brackets is this function of u's and k's and things like this. So let's just set that equal to 0. So that just simply says then that what we have is that u naught n times uk squared plus vk squared minus 2uk vk h bar squared k squared over 2m plus n u naught is going to be set equal to 0. And remember, we also have the constraint that uk squared minus vk squared is equal to 1. Excuse me, not 0, 1. So I've got two constraints. I've got two unknowns for each value of k, uk and vk, and two constraints. So that's good because that means that we can then solve these equations. So let's go ahead and solve them. Now the easiest way to do this is to solve by parameterization. So we know that uk squared minus vk squared is equal to 1. So what we'll say then is that uk is defined to be the cosh of some angle, which I'll call phi, and v is defined to be the sine of that angle, which, so like so, and then that automatically satisfies that constraint over there. So that's great. So now all we need to do is plug into the remaining equation. So the first equation then, which is this one over here. So now this equation simply becomes n u naught times cosh squared phi k plus sine squared phi k is equal to 2 cosh phi k sine phi k times h bar squared k squared over 2m plus n u naught. And well, now we have to use our double angle formulae that we learnt on our mother's knee. So we know that 2 cosh phi sine phi, that's equal to just sine 2 phi. And we know that cosh squared phi plus sine squared phi is equal to cosh 2 phi. So what that means is then I can reorder this equation, and what I get then is that n u naught over h bar squared k squared over 2m plus n u naught is equal to the hyperbolic tangent of 2 phi k. And so that means that if I know phi, which I do from this equation for any value of k, then I can use the definitions over here to compute u and v. So let's have a look then at what the solutions look like. So the way I'm going to solve this equation is by solving it graphically. So we get some feeling for what the solutions look like. So let's draw then on the vertical axis the value of the left-hand side. On the horizontal axis, I'm going to draw phi k, and tan phi k goes between 1 and minus 1 like this. So let's just simply draw what that's looking like. So I really should have drawn this on the other side. Never mind. Yeah. Okay, I messed it up. I'm going to redraw this so it doesn't look terrible. Okay, so then now let's draw the hyperbolic tangent. So it comes in like this. Okay, something like that. And then, so that's this left-hand side over here. And then if I look at the left-hand side, so this thing is nu naught over nu naught plus something or other. And so this thing should be less than unity. So that would be good. But that's only true if u naught is positive. So let's have u naught be positive, and then what I will get then is some value. So let's draw it over here. This thing is meant to be the value of n u naught over n u naught plus h bar squared k squared over 2m. So that's what that value is. And then the solution to this is just the intersection over here. So that's the solution. So what we can see then is that there is a solution if u naught is greater than 0, and then if u naught is negative, then the absolute value of the denominator will be less than the absolute value of the numerator in this expression here, and so that means that there'll be no real solution. Okay, so we know there is a solution, but now what I want to do is I want to beat this down into a more manageable form so that we can actually extract out the quasi-particle spectrum. So our goal is to beat this down into a manageable form to extract the quasi-particle spectrum. So let's do that. So I'll call this step 5, since this is just purely some algebra. So I'm going to use the fact that cosh of phi is the same as 1 over the square root of 1 minus 10th squared phi, and that means that cosh cosh 2 phi is then obviously the square root by the square root of 1 minus 10th squared 2 phi. So that's obviously true, and that means that that thing is that if I write vk squared, so that's obviously uk squared minus 1 from our constraint, and uk squared minus 1 is because of the ways that I've defined, if it is over here, u and v, so uk squared minus 1 is just 1/2 of cosh 2 phi k minus 1. And so I know what cosh 2 phi is from this formula over here, and so now I've figured out then that vk squared is 1/2, and now I can put in what I have for 10th, which is over here. So there's what tanth is. Tanth is in terms of nu naught and h bar squared k squared. So I have v squared is a half 1 over 1 minus tanth squared of 2 phi k minus 1, like that. And so then I can just substitute in my formula. And so what I get then, just without belaboring it, is that uk squared is then 1/2 1 over epsilon of k h bar squared k squared over 2m plus n u naught plus 1. Vk squared is 1/2 1 over epsilon of k times h bar squared k squared over 2m plus n u naught minus 1. So that's the pluses and minuses that we get over there. And what I have for this function epsilon of k is the square root of h bar squared k squared over 2n squared plus 2n u naught h bar squared k squared over 2m, and all of that square rooted. So that's the this is the result for what these quantities actually are. Okay, so we found u, we found v. So in principle, we now have our solution. So now that we know u and v in terms of the alphas, then we can simply now plug that back into our equation for the Hamiltonian, and we will get the answer that we're looking for. So let's do step 6. So now we plug back in, and what you will find is this. So that's our result. So now let's take this result and interpret it. So in other words, what I've shown you is that the Hamiltonian is equal to some energy of some ground state plus the sum over k not equal to 0 of some energy spectrum of some new fictitious particles, these quasi-particles, which are basically this is the quasi-particle representation of the system. So what I have here is essentially a sum of decoupled harmonic oscillators in other words, i.e. Labeled, well, not i.e. Some harmonic oscillators are labeled by k, it's really vector, of course, labeled by k and associated energy quanta. Given by epsilon of k, which we've calculated over here. And so and so this is therefore the quasi-particle energy of the system. Because this thing is just the sum over k of n of k epsilon of k.
Does the way we've constructed these quasi-particles, can we use that to interpret what these quasi-particles are, or is that wrong?
Do you mean, let me say, hold your question.
Okay.
We need 2 more minutes, and then let's talk about that. Let's just do it like that. So, okay. So just to summarize, what I was just about to say was we have the energy of the ground state plus the sum k not equal to 0, epsilon of k times the number operator, which is the number of quasi-particles in the system at time at k. Okay, so what I want to do before I get to the point you're asking, Daniel, is to look at what this energy spectrum looks like. So let's now explore epsilon of k. So let's have a look at what it looks like at long wavelengths. So as I take the limit, k goes to 0. So we now just look at our formula here. So as k goes to 0, what you can see happening is that epsilon of k becomes, as k goes to 0, the square root of n u naught over m times h bar k. And so the most interesting thing about this is that this is linear in k. And because it's linear in k, it represents phonons. So this is a phonon with a speed of first sound, which is equal to the coefficient of that, equal to n u naught over m square rooted. And then if I look at it for large values, so as k gets large, then what we get is that epsilon of k is equal to h bar squared k squared over 2m plus n u naught. And so it has a free particle spectrum shifted by an amount. And it shifted a finite amount by an amount that depends on u naught and therefore is due to the interactions. Okay, so now going back to the question, I think it was Daniel who asked, right?
Yeah.
So you asked, can we tell what the things are? So the best answer I can give you is what I just told you, that namely, the long wavelength limit, we see that the spectrum has phonons in it. So my spectrum looks like this. And then eventually it becomes some quadratic form. So this is the weakly interacting. Gas. And it's not the same as what you have for helium. So what we have for helium, as we know from, it starts off looking like this, but then it does something like that, and then eventually comes up something like that. So this is what you get for helium-2. So, so the helium-2 is of course strongly interacting, and we're just looking at the weakly interacting Bose gas.
I guess I was wondering more, like we've constructed the alpha operators in terms of the A operators. Can we relate the quasi-particles to the fundamental particles? Or like the thing about the quasi-particle being the spectrum being the free particle spectrum for large K, does that mean quasi-particles basically become free particles for large K? Or does that come from something else?
Well, they are free particles anyway. We've neglected their interactions anyhow. It's just a question of
I meant the fundamental.
I mean, you know, they have a relativistic spectrum rather than a classical spectrum. But no, I think the most important point that I think that you should take away from this is that everything, if you look at the ground state energy, you look at the quasi-particle energy, everything depends upon U naught. And so this, everything that you're seeing here is a result of the interactions of the particles. And because we're making a linear sum over K of all these particles, what we are literally summing over is the behavior of all the particles in the system. The alpha Ks depend linearly on the Ks for the real atoms, and so to make a quasi-particle, which is a quasi-particle in K space, it is created by the collective effect of all the other particles in the system. So let me just sort of write down these comments because I think they're important. So the quasi-particles are combinations of all the atoms in the system. So they're collective. And the way that they mix is determined by U naught, which is the original interactions between the atoms.
Is the M here mass of the particle or a quasi-particle?
The atoms.
The atoms, okay.
So then the excitation spectrum epsilon of K describes excitations above the ground state of the interacting system. And not above the free Bose gas. Okay, and you can see that explicitly in the formula here, where the things I worked out has this term and this term, and both of those terms depend on U naught. So what we're looking at is the effect of fluctuations above some many-body ground state. Okay, so that's comment number 2. Comment number 3. The result differs from what you get for helium-2, because we only treated a weakly interacting gas. And we did it by perturbation theory. Okay, so that's the reason for that. The formula for the ground state energy has a divergence in it. And so I need to explain where that comes from and how to get rid of it. So let's first of all see where that divergence comes from, and then let's see how we can solve it. So let's have a look at the ground state correction term. So what I'm talking about here is this ground state correction term here. So this thing here is finite. Okay, obviously, this thing over here seems to be infinite. So let's talk about that. So let's write down what happens for large k. So it is divergent, and it diverges as k goes to infinity, as you can easily convince yourself of. So let's write down what that divergence looks like. So that looks like this. So I take the sum over k, of course, just turns into an integral over k. So the sum over k goes to v over 2 pi cubed integral d3k. And so what we get is v over 2 pi cubed integral d3k, which is 4 pi k squared dk. I don't care about the 4 pi, 0 to infinity. And then the integrand, what I'm interested in is this last term over here, so minus n u naught. So that term is certainly divergent, and so this thing goes to infinity. Everything else is even worse. So obviously there's a problem. Okay, so that's how you can see that there's a problem. Now the resolution isn't particularly simple, but I'm just going to tell you what it is. So this was worked out by Li and Yang, the same Li and Yang who won the Nobel Prize for the theoretical prediction of parity, which also should have been shared with Wu, who did the experiment and discovered that it was correct. But she didn't get the Nobel Prize, but she should have done. Anyway, Li and Yang showed that what they did was when they were the first people to do this, what they showed that if I go to a second order in the Born approximation, then what you get is this. So remember what I told you before was that when we made our pseudo-potential approximation, we replaced the real potential by a potential that is just a constant in k space, and that constant being a k space was just a delta function in real space, and we related the value of that constant, which I called u naught, to the S wave scattering length a. Okay, so this was the scattering length just say S wave scattering length, and then this is was the pseudo potential. And by pseudo potential, what I meant was I replaced u of r by u naught delta var, something like that. Actually, it's not really quite delta var. It's more like, well, it doesn't matter. It's something. It's close to that. Okay, it's more complicated, but don't get carried away with that. Now, the thing that the correction that I want to write down here is that the next correction goes something like this. So this is a series in A, and yeah, it's dimensionally correct, and so when you so the point is that if you include this extra term, which we haven't included, this term over here, oh, bad color. So this term here, when you do all the calculations I've just done, but now include that term, this term over here cancels out the divergences. At the lowest order, and this is like the normalization in field theory. So you just have to do some work in order to see that, and the end result is that you get a finite expression for the energy of the ground state. And I think I'll write that over here. And that's what you get. And luckily, epsilon of k stays the same. And if you want to know where all this comes from, look in Landau and Lifshitz, StatPhys, volume 2, section 25, and section 6. Okay, so and it's not for the faint-hearted. All right, so we can solve those technical problems. So now let's talk a bit more about the validity of the theory. So you can, if you look at this formula up here, so you can see that what we're seeing here looks like the first terms in an expansion, and so if EGS is going to converge as we include higher orders, then we need the expansion parameter to be small. And the expansion parameter is a cubed n over v. So that means we need that a cubed n over v should be very much smaller than 1. So if that's the case, then that's fine. And what does a cubed times nv correspond to? So this obviously means that a should be much smaller than v over n to the 1/3. So i.e. A is much less than V over N to the 1/3. And this thing here is basically the mean interparticle spacing. And A is the S-wave scattering length. And so what that means is that we're in the limit where we have weak scattering. Which also means that the forces are short range. And forces being short range means that the scattering length is much less than the interparticle spacing. Which means that they are dilute. So it's mostly an ideal gas, but every now and then something has a collision, and that's really what we expect in perturbation theory for many-body systems. So the other thing that we've assumed was that we took our potential and we replaced it by this pseudo potential, and we saw that meant that this was valid in the long wavelength approximation. And if you remember way back here, I drew some picture of the scattering. There we go. There's the scattering, and what I pointed out to you was that what we were essentially doing was replacing all the structure by just looking at the long wavelengths and just compressing the potential down into some point. And so by doing that, we are exactly looking at the long wavelength limit. So we're looking at the long wavelength limit. So the upshot of all of this is that when we write down our formula for epsilon of k, we expect that to only be reliable for small k. And that means, i.e., that is why we did not get and could not get the Roton part of the spectrum. So the other point that I want to make, and I don't think I wrote it down in my notes, but I'm going to mention it anyway, is that the ground state that we've computed and the corrections all depend on U0. So everything is a many-body effect. So that's true. The other thing that I want to point out is that I've been saying that we're doing perturbation theory, but we really aren't quite doing perturbation theory. So where did we do something that departed from perturbation theory? Anybody got any ideas?
Maybe when we did the Bogoliubov transform.
Exactly. Why do you think that we weren't?
Because there's no small parameter there, right? We just did a transformation and that's valid over all ranges of k.
Mm-hmm. Yeah.
So it's sort of like redefining your variables to get a series to converge, as opposed to just calculating more terms in a series.
How do you know that gives you more terms? How do you know that that's something to do with convergence?
It's just a guess.
Okay. Yeah, but it's true. So the answer is no, and the reason is because we did this transformation of A going to alpha, and that's known as a canonical transformation. And it was first worked out by Bogoliubov. And so that transformation is definitely not perturbative. So that's where we did something clever by cancelling out the terms in our perturbation theory. So it's not perturbative, but the effect of it was to improve perturbation theory. When I say improve perturbation theory, what I mean by that is that it allowed us to remove a term that could otherwise have been large or even divergent. And so when you start removing divergences or start messing around with asymptotic series and so on, you've sort of entered the twilight zone of the renormalization group, and so later what people understood that this is a resummation. I'm guessing that resummation, go away. I'm guessing that resummation doesn't have two S's in it. So it's something like this. It is also so you could derive it by just a pure brute force Feynman diagram calculation, but it'd be absolutely horrible, and is. And it's also a renormalization group calculation. And I've put in the team chat paper that explains those connections, at least as much as people understand them. Okay, so that's point 7. Let's see, point 8 I want to make. Is a kind of consistency check. So the consistency check is this. So we worked out what epsilon of k is, and we saw that basically goes at small k as h bar k times a number that is the speed of first sound. And so now let's check that this is indeed what we would have expected from thermodynamics. So the way we do that is we say that the speed of first sound is just dp by d rho, the square root of it, so c1 squared is dp by d rho, and then that's the mass density, so that's 1 over m dp by dn, where p is the pressure, and at zero temperature, which is where we are, because everything I've done so far is zero temperature, then the pressure is minus the dE by dV, where Eg is the energy of the ground state, and we already worked that out, and that is 2 pi h bar squared a n squared over n v squared, which is just 2 pi h bar squared a over m times n squared. So that's what the pressure is. And so therefore, if I now differentiate that to get a C1 squared, what I get is 4 pi h bar squared a over m times n. And you'll recognize the thing in front of the n, that's just u naught n over m. And so that's exactly the speed of first sound. Okay, so what I'd like to do now, we're 2 minutes over, and of course we started late because of the APS meeting. So would anybody have be inconvenienced or find it difficult if we carried on for another 3 or 4 years and worked out the finite temperature theory? Why didn't I just leave that to next Monday? Well, I think I'll just leave this to well, actually, okay. So how many people in the class? 17. I think we're already running over. I think we'll just leave this to next Monday. Okay, so you're not quite at the point where I can give you the next part of the homework to look at the finite temperature corrections to this, but we'll do that on Monday. Any questions?